Hey everybody, welcome back to another video lesson. Today I'm going to go ahead and show you how to use the method of initial rates to determine the rate law. Now remember, we're focusing on the differential rate law at this point, which is going to focus solely on how concentrations are going to affect the overall rate of a reaction. So what we have to do, remember, is that we have to use experimental data. So keep in mind that experimental data is the key to solving these problems. So anytime you're going to do a problem where you're going to use method of initial rates, you're going to see a data table with concentrations versus initial rates. So be careful, because we're going to look at other ways of using data with different kind of data to solve the rate law in a different method later. So for right now, we're focusing on how to determine the rate law. And remember, the rate law is written as rate equals K a to a power of m, which is the order, and that's what we're going to try to figure out, b to a power of n. So we're going to try to figure out the order of reaction, which is the m in the n, which will give us insight into how the concentrations affect the rate. Okay, so to do this, we're going to first look at the data here, and we can see that in the first two experiments, we're increasing or doubling the concentration of A while keeping the concentration of B constant. And we're keeping the concentration of B constant because we don't want that to affect the overall rate. So if we keep this concentration the same, we can focus solely on how the concentration of A is affecting this rate. And it's pretty obvious. Hopefully you can kind of see what's going on here, but I want to show you a systematic way to do this when the numbers aren't easy. Okay, so be careful, because a lot of students fall into the trap of just going, oh, I can see this doubles, this doubles. If you see that, that's fine, but make sure you explain it, or you at least show the calculations, one of the two. So I'm going to focus on the calculations right now. So we're going to look at the effect of A on that overall rate. So we're going to look at A's concentration. So what we're going to do is we're going to compare experiments 2 and 1. That's what we're going to do in this one. We're going to compare experiment 2, and we're going to compare it to experiment 1. So I'm going to see how they, just kind of finding the ratio of experiment 2 to experiment 1 is pretty much what I'm doing here. So I'm going to take the rate of experiment 1, or should I say experiment 2, over the rate of experiment 1. That's equal to, and I'm going to kind of basically be playing with this format over here. So I'm going to take K times concentration of A to the m power for experiment 2, and B to the n power for experiment 2. All of that over K, which is the constant for experiment 1 to the m power, and B to the n power for experiment 1. Okay, so the reason I'm doing this is that these are 3 different experiments. Keep that in mind, that these are not a continuation of the same experiment. What they did was they figured out the initial concentration of A and the initial concentration of B, and using the derivative at 0, they found that the initial rate was 2 times 10 to the minus third molar per second. Then they did a second experiment and a third experiment. So these are 3. So this m should be constant for both experiments, for all the experiments actually. So now all I'm going to do is I'm going to plug in the information. Now if we look at this though, we can kind of make some simplifications here. First, the constant is the same, so we can get rid of that because it doesn't change from experiment to experiment. A is the one we're focusing on. B is the one that's going to be constant because it's going to have the same molarity in both of those. So this is going to drop out of this particular experiment because 1.1.1 drops out because they're the same. So what I'm left with is the rate of 2 over the rate of 1, concentration of 2 over the concentration of, concentration of A for experiment 2 over concentration of A for experiment 1. So I'm going to plug in those numbers. Okay, so I've got all the numbers plugged in based from the data. Just be careful with this because you get a lot of students that plug these in the wrong spots. They flip things around. Now I'm just going to use math and simplify everything. And you can hopefully tell, based on the fact that this comes out to 2, this comes out to 2, that m has to be to the first power. So we can determine that this is a first order reaction with respect to A. That's how we would say that. We would say that this reaction, based on the data, is first order with respect to A, and that's how you do it. Okay, I'm going to do B as well, and I'll kind of walk you through that one, and we'll take a look at that. Okay, So we're ready to take a look at how B is going to affect the rate. So we go back and we compare our data. Again, I'm using very simple data here to make this easy to deal with here in the beginning. But again, the numbers can be a little more confusing and it might not be as straightforward. So just be careful when in doubt, just fall back to this method and it should help you to determine what's going on. In experiment 2 and 3, concentration of A is remaining constant while the concentration of B is being increased. It's going up, doubling it. And then we can see that the rate changes as well. So we know that B has some sort of effect. We can conclude right away that it's not going to be zero order. And remember, the orders that we can have for this are usually going to be zero order, first order, and second order. There are other orders, but the AP test tends to stick with those three orders for a lot of the problems they do. All right, so let's go ahead and do the same thing we did before. We're going to just compare experiment 3 to experiment 2. And the other thing I'm going to tell you is that I usually pick the one that has the higher rate to put it on the top because it makes the math just a little bit easier to work with. Again, it doesn't mean it has to be that way, but I find it works best that way. So I'm going to do experiment 3 to experiment 2. Okay? So I'll plug in the data. Okay, so I plugged in the equations, and one other thing I wanted to mention is that notice that I put the 3's on the bottom to remind myself which trial I'm going to be using, which experiment I'm going to be plugging into. Again, not necessary, but again, organization and keeping track of your work goes a long way. All right, so I'm going to plug in the numbers, and then I'm going to simplify it, and I'll get the order, and then I'll talk about it when I'm done. Okay, so we can see that with B, the reaction is a little different. It's not going to be a first order reaction. Now it's going to be a second order. So with respect to B, the reaction is second order. With respect to A, it's first order. And that's how we say that. And we say overall to the whole experiment, for the whole equation, for the whole reaction, I should say, is going to be third order. So we say it's third order with respect to the chemical reaction. First order with respect to A, second order with respect to B. Okay, so there you go. That's how you use the method of initial rates to find the overall rate law for a particular chemical reaction. One last thing I'm going to show you before we go is how you solve for K, because usually with these questions they're asking you two things. They want you to find the rate law, and then they want you to find the rate constant with the appropriate units, and that's the part that a lot of students have trouble with. They forget to put the units. So I'm going to focus on K in the last part of this video, and we'll take it from there. Before I do that, though, I just remembered there was one last thing I wanted to mention. Notice that I crossed off A in this experiment because A was staying constant. I didn't actually need to do that. I could have kept A in here because notice that I know what the order of A is. I could have easily plugged in a 1 here for M because I know M at this point, and I could actually have solved for A and incorporated that into the numbers here for B, and actually not into B, but I could have brought it over here and incorporated it into the rates on this side to help me solve for this. So that's just a little key or a little trick on some of the more complex AP questions. Once you know the order of 1, you don't have to have these all stay the same. So just a little tip I figured I'd throw out there. All right, so let's take a look at how I calculate K. Okay, now I'm ready to solve for K. So to solve for K, what I'm going to do is I'm going to use the rate law that I determined already. I know that it's first order with respect to A and second order with respect to B. So now all I need to do is just pick one of the three experiments in this case and plug it in because K should be constant, and no matter which one I pick, I should get about a relatively same value for K. Now it might change a little bit depending on rounding and how closely this is to real experimental data, but that's it. I'm just going to plug in and solve for K. Now what I like to do is I like to rewrite the equation in terms of K. Okay, there's a couple reasons I like to do this. One, it makes it easier to solve, and two, it helps me to focus on the units a little bit more. So all I'm doing is bringing A to the first power and B to the second power and putting it underneath the rate. So just dividing by both of these and putting it on that side. All right, so first thing I'm going to do is I'm going to focus on the numbers, and then I focus on the units because I need two things. I need to know what the value of the rate constant is, and I need to know the units. So I'm going to go ahead and plug in the numbers first. Okay, so now I plugged in the numbers. Normally I would say yes, you should be using your units here, but I personally like to do the units off to the side on its own, and I'll come back and do that in a second. First thing I'm going to do is just simplify this and get the answer. Okay, so after doing the calculation here, you should end up with 2.00 using significant figures. Now to get the unit, what I'm going to do is come over here and just plug into the same equation, but I'm just plugging in the units. Okay, so now I plugged in my units. Notice that the molar, first of all, I changed my molar per second. Notice it's molar per second to molar inverse seconds because it's just a little bit easier to deal with the fraction like that. So I'm going to cross off molarity. What I'm left with is seconds to the minus 1, molarity squared. So therefore, if I write this properly, I'm going to have molar inverse seconds and, oops, I should do the, all right, so if I write the units in, I'm going to write molar to the -2 and seconds to the inverse 1. And there you go. There is my constant for K. Now I can plug that into K in my expression, and now what I can do, since I know all of this, I can now come back to this experiment and say, okay, what's the rate of reaction going to be if I have, whatever concentration I currently have? I'll plug those numbers in, plug in my constant, and I can solve for the rate at any point from this point forward. And this is why this is important to know, because now that we know this rate law, it's going to give us a lot of power in using it in future experiments with this particular chemical reaction. And keep in mind too that the rate is now characteristic of this reaction. This rate won't change. This rate law is always going to stay true for this reaction until something, some sort of major change happens in nature or science. Okay, so there you go. There you have it. That is how to use the method of initial rates to find the rate law for the overall reaction and how to find the constant with the units. All right, thanks a lot, guys. See you soon.